Eventually, we're going to get into a topic in this course about logical and physical topologies. And there's nothing worse than trying to clarify the difference between the two. I'm a physical guy. I like to see things in action. I hate abstract talking. I hate things like data structures and things of that nature because if I can't see it, I'm not going to understand it. But then I come to this point where it's like, what's the difference between physical and logical? I'm talking about topologies. When I say topologies, what are you guys thinking about? Pictures? Maps? Models? Okay, that's all we've been talking about, it's models, right? And so we have, starting with the data, we have segments, packets, these are our PDUs, of regardless of what model you use. Then we have frames, then we have bits. The signals, if you will. What we're going to be doing today, and listen up, because this will affect everybody in this classroom, I got to establish some rules so we're all on the same page. The person who sits here, sole responsibility is going to be a gateway. Each one of our rows is going to represent a network. Okay? What does a network consist of? End devices, intermediary devices, and connections. Correct? What we're going to try to do is we're going to try to send this puzzle, this picture, if you will, to Dominic. Now, we got to be really careful that we follow the rules. Because if we don't follow the same rules, the message isn't going to get to where it's destined to get to. Okay? So I'm using this physical environment. I'm trying to map it out. So the way our physical environment looks like is something like this. And then we have a person here, a person here, a person here, and a person there. Correct? And we got another row. Person here, person here, person here, person here. And we have another row. Likewise, person here, person here, person here, person here. I need to be able to identify you guys both logically and physically. Let's talk about physical addresses. How could I use to identify? What would you guys use to identify these rows? Come up with a system. Okay, that's going to identify the seat, right? The first number in there should identify the room, C002. Whip-de-doo. I'm in the room, but I need to identify the rows. Yeah, let's keep it simple. R1, R2, R3. Great. So I went from the room being C002 into here. Now I identified a row. I need to identify you uniquely. I need to get right to your seat because I got to get this message to Dominic, who's the back of the classroom. So how do I identify the seat now? Where do you want to start? 1, 2, 3, 4, or 1, 2, 3, 4? Left or right? 1, 2, 3, 4. So for you to identify a seat in this classroom, doesn't have to be a person, just a seat, you are going to say R1 seat and then the number, right? This is our physical address. What about logical addresses? Now it gets cute. I have a John here, right? Terry here. Ben here. And sorry, I missed Jesse. So my system's a little screwed up. I should get to know my surroundings a little bit better, but you guys get the rule. The formula is flexible. Oh, hell, you're going to do this to me. I was doing pretty good, wasn't I? First letter. Chad, first letter, though. That's all I needed, just to see. It would have worked. So you guys are going to have to get to know each other logically. Now, where'd you come up with your logical names? Mom and dad said, you look like a Terry. Look how cute you are. They didn't say tall kid with a bunch of hair on it, right? That would be a physical description of you. They decided to give you a logical name because to them, it made logical sense to call you whatever, right? And that's it. That's what our protocols are. Protocols are a set of rules. And so in our country, we say first name, middle name, last name. My mom doesn't have a middle name. And in Italy, they just do first and last. And in some countries, some cultures, especially way back in the day, and I think that happened in our country too, you were identified by your job occupation. Especially if you came from overseas, because your last name was usually the town that you came from, or something to that effect. And so when you came over here, sometimes that carried over, sometimes it didn't, so they asked you what was your occupation. And if you were a bricklayer, you became bricker, or something like that. If you were a blacksmith, you might have became smith. That's why there's a whole lot of smiths. So these are rules, these are protocols that establish names. And I'm doing that right here. I'm saying that your logical address is going to be your first name, okay, folks? But we have a problem, don't we? I got two Johns. John, how do you spell your last name? Louder and slower. Oh, Martin, I didn't know what it was. Thank you. So, anybody needs to send anything to John in the back of the classroom, you're going to use his last name. Do I have any other conflicts? There's only one David now, right? So I just need to work that out. We got that out. Because remember, no two devices on the same network can have the same logical address. Correct? All right. That's the physical topology of our class. Another thing we're going to identify is what seats have what responsibilities. If you sit here in this aisleway, so if you're seat number 1, you're going to become the gateway to your network. Each of these rows represent a network. For those that are in the middle, you guys are the switches. So you guys are just going to be one big giant switch. For those in the very end, you're the PC. The only difference is that Dominic, you're the server. Right? Because PCs, clients make the request and you have to be the server. He thinks all high and mighty of himself now. I elevated him to a higher standard because his logical topology looks like this in his head, guys. But you know what? We can pop his bubble. He serves us. See? So he's our servant. So now we just flipped it. See? I do that all the time with students that just feel like they're above the rest of us. Okay. Now, how does this look with network stuff? This is the logical way of doing it. We have a router connected to a switch, and from the switch, we have PCs. These routers are going to be connecting to each other. Logical topology, something you guys have been seeing in Packet Tracer. Physical topology. Hopefully that clears that up, so by the time we get to that chapter, you guys have a pretty good understanding of the difference between logical and physical. Logical is all about the behavior of how this is going to act. Physical is the nitty-gritty stuff. Where the wires are connected to, what interfaces are being used, where things are located in the physical environment. All right. You guys are going to be getting a bunch of different types of envelopes. I need to identify each of these envelopes. Let's do it in series. So, not as many in this class. John, can you pass this set? Let's not get carried away, Nick. Christina, pass it to Dominic. I know. I didn't say I was going to interchange your name. Pass it to Christina. Yes. It's interesting. Last in the link. Is that correct? No, it doesn't have to be. No, just in this topology, it so happens to be. Most of the time, the server's out there. But in this classroom, the way it's working is I just pick that person. It doesn't have to be at the end of the link. Because this person's hooked up to a switch, and the switch can have multiple devices on there, so it doesn't, just think of it as like a circle. There's no ending and no beginning. No, sorry, Jessica, ooh, that's twice. I'm going to get the evil eye. Christina, you get one of those. Yeah, so each end device is going to have a series of envelopes, right? Because each end device has this stack, this protocol stack installed on them to understand it. Intermediary devices will only have so many levels. If I'm dealing with the switch, that's those guys in the middle, you guys will come up the frames. If I'm dealing with the guys at the end, you guys are routers, you guys will come up here. But end devices will have the whole stack. Okay? We're good with that? All right, so the way this is going to work is that we want to offload processing. I don't understand what people get by doing puzzles. That's like paying for punishment. I'll give you $100, slap me with a belt. Oh, sure, $100, I'll spank you. I just think that's crazy. And so people that go to Walmart and they buy puzzles or wherever and they buy the ones that are like 10,000 pieces, I'm like, somebody keep an eye on that psycho. Because I just don't understand that. But it does, it does sort of pertain to our class, right? And that is, that picture gets broken up to a bunch of pieces, correct? And so what we're going to do is I just want to give a handful of pieces to just Christina and just you, okay? Now Jacob, sorry, not Jacob. No, that's just you. All right, take your time, pass this down, give it to Dominic. Just work your way down the routers, and then they'll work their way over. I did the work for you, you're welcome. All right, so the idea is you guys want to offload some of your load, and you're like, I got a bunch of these pieces here, and what I really need is I need somebody to put them together for me. And we call this like cloud computing, right? Because we assume that a company like Google is going to have millions and millions of servers, it's going to have a lot of processing power, so that we can offload stuff that takes a lot of time, give it to the server, and it should take less time, right? So the concept is you have pieces. Just consider all those pieces as one entity. That's the data. So all these things grouped together is the data, correct? So all my PCs, what you're going to do is you're going to take that data and you're going to come down here to layer 4, the transport layer. And what do you want to do with that data? Break it up into pieces. So just separate them on your desk. All right, so you got them all in their own little pieces. What's the next thing you need to do with this TCP protocol if we follow that? Okay, well, we need to encapsulate it, right? And we need to decide how many of these pieces we can put inside the white envelope. So let's try, because this is super Dominic, we're going to inundate him, and we're going to try giving him 2 pieces at a time. Right? Sometimes we might have to scale back and only give him 1 piece. Other times we can say, you know what, screw you, you're getting all of them. Taking the assessment early, right? So, you're going to jam them all into that white envelope. Do not lick it. I don't want you guys to get some kind of disease. Just close the envelope so you got this. But, yeah, only 2. I only did all of them because I don't like them, but you're going to give them a break and only do 2 at a time. All right, so only 2 at a time. But now, what do we put on this? So we just encapsulated the data into a segment, right? But the segment has a header. What do we put on this envelope? If you guys were to send this to your brother, what would you put on there? You got a sender up here and the receiver right there. We got addresses. All right, what addresses are we going to use? What are they called? Port addresses, right? And our port addresses have to identify the application above us and the service it's going to, right? So if I'm submitting this to a web server, I'm going to write a big fat what? What's the default port address for web service? 80. So write a big 80 in the center of your white envelope. Now, John, you are going to put 1,025 in the upper left corner of your envelope. Christina, getting better. You're going to put, 49,285. I don't care, just make some random number. Notice I picked a number over 10,024. And I can go up to 65,535. They're randomly assigned because, 1, those are separate computers. And the operating system has to identify all the different applications that are trying to access the stack, right? So you have a web browser open up. I'm your operating system. I told you to use 1025. Christina has a web browser open up, and I said, you're going to be 49,000 something, 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 right? You'd have been really impressed if I remembered that, but I couldn't even get your name right today, so don't expect too much from me. All right. We got our segment. If we're using TCP, we'd add more stuff to this envelope, like sequencing, like acknowledgements, like control flags. When we get to that chapter in our book, we'll come back to this envelope, and we'll add more to it. But for today, it's about the process, encapsulation. Now, what's the next step it's going to go to? It's going to go down to the network layer or the inner network layer. You guys call it? You guys should have, and thanks for my volunteers, a flat orange envelope with 2 white labels on there, correct? Fresh labels. See why you guys did this now? Because now they can write things in it. Take your segment and stuff it inside that. This takes time, doesn't it, guys? But each of this process has a purpose, has a function to it. All right, don't lick it. Don't even get cute and put the little metal thing in there. It just takes more time. Just seal the envelope or close it. All right, you guys have white labels. What are we going to put here? IP address, but we said we don't have IP addresses. We got to put a logical address. So our rule is, if you're John, you're going to write John in the upper left corner of your envelope, right? What are you going to write down here? And which is Dominic. So John, Dominic. Jesse, no, Christina, and Dominic, right? Of course, IPv4 has a bigger header for other things, but just the process. You guys are going to take this packet. That's what this is called. This PDU is called a packet now, right? And now you're going to make it into a frame. You take this, put it right in there. You notice this envelope is different. A little bit more heavy duty than all the other ones. The other ones are flat, made out of paper. This is made out of plastic and it has bubbles in there. Why did I go waste my, I think these were like $5 a piece. Not security as much as durability, in the sense that this is going to go out in the physical world. So it could be trampled on likewise. So we got to create a frame. So we're framing this data. And in there, remember there's a trailer and there's a header to let us know where it begins and where it ends. But there's also a mechanism to check for errors. So, you know, they say before you open up the box, check for scratches and dents and anything else like that. Likewise. So I made it a different, heavier duty, bigger frame because I just wanted the durability. Likewise, that's what happens at the data link layer. But guess what? You got white labels. Now you need to put physical addresses here. What address do we use? It's very conditional. You got to ask yourself one thing. Is the server on my network? And the way we do it with IP addresses, we look at the network address and we compare it to our network address. And if they're not the same, then I say, hey, if I say C01-01, you guys are automatically saying that for me to get to C01, I have to go through that door, right? If, on the other hand, the server is on your network, that is me saying if there's a student in this classroom, I shouldn't have to leave that door. So it's conditional. Does it stay within my network, within my row, or does it go out of my network? And if it goes out of your network, you must send it to the place it goes out of. So in other words, all of your packets, your frames, need to be sent to your gateway because it's going back there to row 3, and nobody on row 3 is communicating with any server. You guys are row 1, row 2, network 1, network 2, correct? So John, Christina, what you're going to write up here in the upper left corner is, for John, it's R1, seat 1, 2, 3, 4, 5. Christina, yours is going to be R2, seat 6, right? You guys are going to write your gateway's MAC address. How does your computer know that? Because you have to configure your computer to have a gateway address. And that gateway address has to be on the same network as you. You'll see this in Packet Tracer, and they have a big mistake in this. So the people that had my lab yesterday know what I'm talking about when we were configuring our devices. Now, your computer is going to have a MAC table. And that table is going to have an IP address of your gateway mapped to the physical address. This is the logical meeting the physical, right? So at this point, what John would do is go to that table and find out where his router is. And his router is R1 seat 1. And you're going to write that down. If he did not know that, he would send an ARP request, pausing the communication process, saying, hey, Chad, where are you? I know you're my gateway. And Chad would say to him, I'm in row 1, seat 1. And then he would store that in his table so he doesn't have to ask that damn question all the time he wants to send out this. Because he's got other pieces to be sending, right? So store that. So now you got R1, seat 1. Christina, R2, seat 1, right? Now, you can't get off your seat. You got to sit where you guys are. You should be connected because 2 or more devices connected together, right? So the people in the middle, you guys are going to act like switches. So, pass your frame. No, you don't know about that. You don't know how to get there. You're not a gateway. You're a PC. The only thing you know about is Terry, right? Likewise, the only person that, just wait, just hold still. Now that's in the switch area, the switch understands frame or physical addresses. And the first thing the switch is going to do is going to look at the destination MAC address and see if it has it in its table. And what it's going to do, it's going to map its MAC address to the physical port that that address is set on. If it doesn't know where that gateway is plugged into, it's going to broadcast an ARP request again. And then the people that aren't routers are going to say, that's not me, ignore the message. And the port that has data coming in on it must be the router. And now you're going to map that physical address to the port that that router's plugged into. Translation, now you know who to send it to. So this is why you need to hand still. Terry is going to hand it to Jesse because Jesse's connected to the router. You see what I'm saying? Terry's connected to John, the PC. Jesse's connected to Chad, the router. Kyle, you got to hand it over. And you can do this because you're allowed to get up off your seat because it's within the switch, right? You're going to hand it over to, oh gosh, that's hell. I was doing so well. Is it Michael? No. Oh. Josh. Damn, I always do that with Josh. I'll get it. All right, now you guys are going to now pass it to the router, right? Notice you didn't rip anything apart. You might have regenerated the signal so that you can go longer distances, but that was it. But some people got stepped over because you guys are ports for other devices that might not have been used. Make sense? All right, now it's at the router. The whole idea of the router is tell the packet where to go, left, right, up, down. So in order for it to do that, it's got to de-encapsulate the frame. So all my people over here, open it up. You're allowed to. The protocols say that. And now you get the packet, right? So you just got them de-encapsulating. So you're going up the stack. So you remove that, and now you're stuck with the packet, right? Are you going to open that up? Tempting. Could be $1 million in there. But it's not addressed to you, correct? The only thing you're going to look at is the R number. Well, you don't have that, right? Because that's the physical stuff. What you have is the names. So it's Dominic, right? You guys have that for the destination. And you're going to say, well, Dominic's not on my network. And Dominic's not on my network. I'm going to pass it to a router that might know about Dominic or might not know. Like I said, this router, Chad, is connected to David. David is connected to John or Martin. Correct? So this is the way it's going to happen now. You looked at this, and you have to create a new frame. So here's some white labels. Can you pass this back to David? You guys are going to take your white labels, re-encapsulate the packet. So go ahead, put the packet back in the frame. But this time, you got to change the physical addresses, right? Because the frame is at a different physical location. So you're going to take your label, stick it over the destination, stick it over the sender or source, and now you're going to write what for the destination? If you're Chad, what are you going to write in there? R2 seat 1. If you're David, what are you going to write in there? R3 seat 1. What are you going to write for source? Your position you're currently in. R1 seat 1 for this one, R2 seat 1. Right? Dominic, question. That happens in local delivery only, not across the WAN, not across the public network. Otherwise, we'd get nothing done. He's taking a guess. He's saying, I hope this person knows how to get there. I don't know for sure, but he's taking a guess. This person's taking a guess too, that I hope this person knows how to get it there. So, turn around, guys. Pass it to your router. Just set it on their table if they're not looking. All right, now, Chad's out of the clear. Kyle, question. Ends up in garbage can of cyberspace. That's why every packet has a time to live field, so that they self-destruct, so they don't go around in loops and loops and loops. Good questions. So now, David and now Martin got the frame. They're gonna open it up. Oh, can you pass? Oh, you're almost out. Pass your labels back down to Martin for me, please. Sorry, so he can re-encapsulate. Question. When that happens, does it just resend it? That's what TCP is all about. Because TCP will get an acknowledgement back from the server, and it'll say, I guess you didn't get it, so I'll have to redo it. Very good. But UDP wouldn't. UDP says, tough luck. But you see the overhead and the whole stopping and going deal. UDP is doing best effort. So that's why it's very time sensitive. Make sense? All right, so the other routers are getting this. And what's going to happen is if I am row 2, seat 1, I'm going to say, well, Dominic's not on my network because I don't know about this address. So I need to re-encapsulate this. So he's putting it back in his frame. But now he's going to write in here, destination's going to be the same, but destination is now going to be R3 seat 1. And source is going to be R2 seat 1, right? So he just re-encapsulated that. But Martin's going to do something different. Martin's going to say, yeah, I know about this guy. He's a pain in the ass, and he's at the end of my network, and he's constantly bothering me, right? So now what he's going to do is he's going to reframe the packet, but he's going to write the destination, R3 seat 6, source, R3 seat 1. And now that frame should get to him. But first it's got to go through the switch, and the switch plays its games, which so happens to only be these two guys, so you won't frame anything. Yep, you'll pass it, and then finally gets to Dominic. When it gets to him, and you're going to pass it to Martin, he's going to do his thing. Now Dominic deframes it, so he takes away the encapsulation. And he's out here, and he says, oh, that's me. I get to open it up. And now he opens up, and he gets the segment. Now what he's going to look is to see if he's got a service that identifies with port 80. If he's got that service running, and he goes, I'm going to open this up, and then I'm going to get all these pieces together, do what I need to do with them, pass up the data to the application layer, to the service does its thing, and then now he's got to take all that pieces and break it back down, but it's been processed, send it back to us. And he'll take the source stuff and switch them. He'll take only the logical stuff. He'll take the destination IP address and switch it to become the new source. The source IP address to be the destination. So you're switching the source and destination. So this way it can make its way back. You're going to do the same thing with the port address. You're going to switch the destination port address with the source. So this way it goes to the right application that made the request. What about the MAC addresses? You don't switch them. You generate them on the fly like we were doing. Depending on where it's at in the physical world, it gets new addresses. But we use the logical addresses so we can get it back there and put things back together and identify the right application. How do we do, guys, to just take that logical abstract model called the OSI model and break it down into the communication process on a level that Seems a little elementary. We're working with physical things, pausing it. You see the time it takes? What if everybody on this network was trying to talk to the server? Like everybody logs into these computers, they go over to the server, and you notice your desktop's taking a long time. Well, poor Chad, poor David, they're going to be inundated with all these envelopes. And they got to start finding places for them. And what's going to happen is these envelopes will self-destruct. If David doesn't get to it within so many milliseconds, in the garbage can it goes. Now the server's going to say, well, I was expecting packet 2 or segment 2. So I better send it back to the person saying, look, something happened, resend packet 2. But this time when you send it to me, don't put the whole damn puzzle in one envelope. Control your flow, throttle it back so that we don't inundate all the intermediary devices. This is why we like to have faster processors on our routers and more memory. Okay, guys?